right, everybody. I think it's about 4 o'clock on the dot. Hello and welcome. I hope that you guys have been staying dry today and not blowing away in the wind that's just outside. It is really, really whipped up out there a little bit. Anyway, we'll stay nice and toasty and warm in here at least for an hour or so. Quick announcement. So I am going to leave campus kind of early today because I have a massive stack of papers to grade. But I am going to go downstairs for just a bit after class. So if anybody wants to talk to me about anything about this class, stop by relatively quickly after class and I'll still be there. By relatively quickly, it kind of just depends on how many people are there. If I go down there and I wait 20 minutes and nobody's there, I might just decide, all right, grab the papers and go. But if there's a bunch of people wanting to talk and ask questions, I'll stick around for a bit. So that's no problem. But I will definitely answer emails. And I will also definitely be around tomorrow evening. By that time, I should be done with all my grading if things go as planned. So, but you don't have to wait till 8 o'clock tomorrow night. You can send me an email with questions. I've really been appreciating all of the interactions that I've had, especially it seems like it's been increasing, maybe because the test is coming up. But there's been more and more activity on my, both on Zoom and in person. So just kind of keep that up in terms of my office hours. There is the homework that's due tomorrow night. I think that's what most folks are working on. And then we'll have just one more assignment due next Friday before we get to our exam. Next Friday's homework will be based on what we've been doing this week, which we're going to finish the stuff for the exam today, actually. I'm usually not this good. I'm usually like, all right, I'll teach the material, and then 2 days later, we'll have a test. This is more like I'll teach the material, and we'll still have like almost 12 days or something to kind of have time to sit with the material. So that hopefully will make it a little less pressure and a little less stress. But yeah, there will be the one more assignment coming for next week. And then we'll have a little bit of a break. The following week, we got the exam on, I think, on the Tuesday after that. So, all right. Any questions about any of that? Okay, well, I've got some group work for us to do today. I had a real hard time solving my own group work. And that's because I, for some reason, thought that that this was true, and I was bound and determined to make it work. And you would think after 5 minutes of struggling with this that I would figure out that there must be something wrong. This was supposed to be 143, but actually the number that's on the group work is 133. So I'll just save you guys the misery that I just put myself through and give you the correct factorization now, which makes the problem a whole lot easier. So keep that in mind. In a few minutes, we'll do some group work and you'll already have a leg up compared to how I was doing with the problem. Anyhow, it's a nice group work that is going to show you, again, what I kind of bragged about on Tuesday, which is putting the Fermat's-Little theorem together with the Chinese remainder theorem. Both theorems working together to solve congruences in moduli that are not necessarily prime. But often what we will do is break down a modulus into its prime factors. This is what I talked about last time. It's a very common theme. And we will break it down into its prime factors and then use Fermat's-Little theorem in each of the individual prime factors. In other words, take one semi-difficult problem and break it down into a series of easier problems where we have more tools that we can use, such as this one here. Right, so I mean, this is one of the crowning results of number theory, honestly. So this is something you want to keep with you the whole rest of the semester, right? Fermat's-Little theorem. If we take a prime p and a number that's not a multiple of p, then we can raise that number to the p minus 1 power, and it reduces down to 1 in mod p. Really good way to reduce powers of numbers in congruences. So it's a really, really handy result. We gave 2 proofs of it on Tuesday, and we certainly did some examples of it, as well as kind of see what kind of applications it could have. So I felt pretty good about kind of where we left off with that. I want to talk about a different theorem today. It's not quite as famous as Fermat's-Little theorem, but it is in the same spirit. It certainly makes sense to talk about it at the same time because it involves congruences in mod p. And it is called Wilson's theorem. So let's just do something a little new here. And we'll tackle this result. And then we'll be using this theorem to finally go back to what I kind of advertised originally, which was that in this chapter, we were going to start solving congruences of polynomials of higher degree. So, Anthony? Yeah, this is all just in chapter 5. This is actually, if you want specifically, this is now 5.4. So, yeah, thank you. So 5.4, Wilson's theorem. Okay, what does this say? It just says, let P be a prime. In this case, what we can do is make the following claim. If we take P minus 1 factorial, so I'm going to use a combinatorial expression here, P minus 1 factorial, that turns out to be congruent to -1 in mod P. So P minus 1 factorial is congruent to -1 in mod P. So this is the Wilson's theorem. And I am going to prove this one also. You can see why it's maybe not quite the same thunder of the Fermat's Little theorem, because, Fermat's Little theorem, you can take any number A. It's not a multiple P, and it gives you a number of statements here. But this is just a straight fact about, about prime numbers, basically. Okay, so to do this proof, the first thing you do is you just prove it directly for P equals 2 and 3. Okay, so P equals 2, you're just getting 2 minus 1 factorial, and that is just 1. And in mod 2, it's a congruent to -1. So that checks out there for P equals 2. And then we also can check P equals 3 just directly. So 3 minus 1 factorial, which of course is really 2. 2 is also congruent to -1, and that being in mod 3. Okay, so you could just write that down as for starters. And now we're going to really get to the heart of the proof, which is what happens when P is bigger than 3. So now I'm going to assume that P is greater than 3. It's a prime, but now it is greater than 3. Okay, and we're going to, look at, so let's just consider P minus 1 factorial. Okay, so just writing down what the theorem talks about. This, of course, is just 1 times 2 times 3 and so on. We're multiplying all of these together times P minus 2 and times P minus 1. So we just write that all out, as I'm sure you guys know. I'm going to pick some number in this list that's being multiplied together. So I'll call it little a, be one of the numbers in that set, either 1 or 2 or 3 or anything up through P minus 1. Now, obviously A is less than P, so that means that it will have no common factors with P, right? So the GCD of A and P would be 1. There's no common factors between the A and the P here. And because of that, since that's the case, then the congruence, we're going to go back and use our theory of linear congruences again. So the congruence, and I want to look at the congruence of AX congruent to 1 in mod P. Okay, so you guys probably remember when does this have a solution? Well, it's as long as the GCD of A and P divides B, which it does. And in that case, the number of solutions is, it's unique modulo P in this case, right? So this congruence has a unique solution for X. Yeah. Again, for those of you who enjoyed the group theory conversation on Tuesday, you can just imagine that you're working in the group of non-zero elements of mod P. A is a non-zero element, so it has to have an inverse. And so A and X are inverses, in this case, multiplicative inverses of each other in this group, which is called ZP star. Right. So there is a unique solution for X. Now, in two cases in particular, the unique solution is really obvious. So if A is equal to 1, then obviously X is also equal to 1. That's just clear. And also the other obvious case is that if A was equal to P minus 1, now that would be essentially saying that A is equal to -1 in mod P. Well, then your unique solution is also going to be, it's going to be -1 as well. So actually, sorry, I'm gonna write it as P minus 1. Of course, these are just unique modulo P, so I can write them in any congruence notation that I want. What I'm trying to say is that, you know, the A matches with itself, the P minus 1 matches with itself, but everybody else, what I'm going to claim now is that everybody else has a partner, i.e. an inverse, that is not the same as itself. Okay, so let's see if I can convince you of that. Is everybody good so far, though? All right, so now let's just imagine, so suppose that 2 is less than or equal to A is less than or equal to P minus 2. So we take any of the other A values besides the extreme cases here, and we're going to kind of look at this case. In these cases, my claim is that the X that solves our congruence here is not the same as A. It was the same as A for these two values, but not for any others. This is kind of what I'm claiming. Okay, so let me do sort of the little proof of this claim as a sub-proof, so to speak, here within the main proof. I'm going to do this by way of contradiction. So by way of contradiction, if X does equal A, then, well, then your congruence just becomes A squared is congruent to 1 in mod P. Okay, and this means, I'll just say, so that P divides A squared minus 1, or in other words, P divides the product of A minus 1 and A plus 1. Righto? So P would divide this product, and since it's a prime, and then it would have to divide one or the other of them. Yeah, so this is pretty elementary, actually. It's just saying all of the right things. So P divides A minus 1, or P divides A plus 1. That's because P is prime. I won't write that down, but that's basically the gist of it. So then you can say, well, if P is dividing A minus 1, A minus 1 is somewhere between 0 and P minus 2. It has to be actually 0. So that tells me that A is equal to 1. Or the other case would be if P is dividing A plus 1, let's take a look. A plus 1 is somewhere between 2 and P. So it must be that A plus 1 is equal to P. And that means that A is P minus 1. And that's a contradiction because look what I supposed at the top of this little part of the proof. Okay, so that is the contradiction. Now, we're still proving Wilson's theorem. Let's not lose track of it here. We're looking at this big product here. And guys, if I take any number and I multiply it with its partner, its inverse, they cancel, of course. That's what inverses do. They cancel out. So if you just take this whole product and say, I'm just going to find everybody with their partner, right? Now, the first one doesn't have a partner. It was if A equals 1, and its partner was itself. And the last one does not have a distinct partner. But all of these other ones in the middle, guys, they all have an inverse that is something other than themselves. So we can put those together and then cancel them out, essentially. That's how this proof is going to work. So in other words, what we're saying, let's just write this down. The conclusion is, so this is the end of the proof of that claim. Yes. Was there a hand up? Yeah, Kim?
Right, A is equal to negative.
I could, but I sort of set this up that I just wanted to start off with A being in this collection because I'm going to be considering A to be these numbers in this list here. Yeah, that's the only reason. Yeah. Okay. So the numbers 2, 3, 4, and so on up to p minus 2 can be put into pairs. I'll write the pair as A comma X, I think. So it's a good notation for that. With A distinct from X and AX congruent to 1 in mod P. That's right. And if you are comfortable with this, I'm going to do an example in a second. I'll pick a specific one. But what I'm basically going to tell you then, guys, is that if you take 2 times 3 times 4 times ... times p minus 3 times p minus 2, and you multiply this out, just this part of it, everybody is going to have somebody else that cancels them out, right? In other words, in mod P, everybody has a partner that cancels them out. So this product cancels out in mod P. It cancels out in mod P. And so P minus 1 factorial in mod P, all of the part in the middle here, guys, has canceled out, and you just have 1 times P minus 1. Those are the only two numbers that did not cancel out in mod P. And of course, P minus 1 is the same as negative 1. So that's the end of your little proof there of Wilson's theorem. P minus 1 factorial has to be congruent to negative 1 in mod P, always. It's another one of those theorems that you can use to prove that a number is not prime. Because if this congruence fails to be true for any particular number, then that number can't be prime by the contrapositive of this theorem. So just as a quick example, is everybody okay with this? Hopefully I'm making good sense. I gave an exam today in my other class, so this is as rusty as I've been teaching all semester. Usually I've only had a 1-hour layoff before I come back in here again, but it's been 2 days. I haven't talked to anybody since I talked to you guys. Okay. Anyway, so as an example, let's prove that 16 is not prime. In case you didn't know that. 16 is not prime because if you look at 15 factorial, 15 factorial in mod 16 is actually congruent to 0. Everybody believe that? That would just be saying that 16 would have to divide 15 factorial. Do you think there's at least 4 factors of 2 inside of 15 factorial? There's a lot of even numbers in there, guys. Each of them gives you factors of 2. So yeah, so this basically is, so the application here that I'm showing with this example is that if n minus 1 factorial is not congruent to negative 1 mod n, then n is not prime. So if you find some modulus that has this the failure of that congruence, then that modulus must not have been a prime congruence to begin with. Yes?
Why don't you choose fixed factorial?
Well, I could have used other examples. Yeah, I just wanted to pick one that wasn't too small. Yeah. Actually, let me do an example maybe with let me see, what number do I want to pick here. Let's do let's use a prime that we can apply this Wilson's theorem to. So let's take the prime 23, right? And if we look at all of the factors from 1 through 23, what this proof is suggesting is that we should be able to pair them up, right? So 23 factorial is equal to, so now I'm back to illustrating the proof again. This was just my quick little contrapositive thing. Now I'm going back to the actual case of a prime. What this proof is saying is, well, I ought to be able to take all of the numbers between 1 and 23. I'm going to do it right here, guys, so leave a little bit of room. Actually, make sure you leave plenty of room because there's 23 numbers here. 1 is going to be all by itself. 23 is going to be all by itself. But every other number, the numbers that are between 2 and, oh, I didn't mean 23. I meant 22. This is supposed to be p minus 1 over here on the end. Yeah, right? So we stop at p minus 1. But every other number between 2 and 21 can be partnered with somebody other than themselves. So could somebody help me? What would be the partner for the number 2? Can you do it in your head? 14. I don't think it's 14. Oh, 14. What do I have to multiply 2 by to get 1? 12, right? 2 times 12 is 24. Well, in mod 23, that's just 1. So I'm going to put the 12 there. So 2 goes with the 12. Let's try another one. Can anybody think what the partner for 3 would be? Again, we're working in mod 23, so the numbers are a little big. Any thoughts here? Yeah, 3 times 8, right? 3 times 8 should cancel out. Okay, let's go to the next one. 4. Any thoughts on what a partner for 4 would be? 6. It's actually 6. 4 times 6 is 24, which is 1 in mod 23. Let's keep going. Partner for 5. Oh boy. 9. Pardon? 9. 9. So 5 times 9 is 45, which is -1. But if 5 times 9 is -1, I'm pretty sure that 5 times -9 would be +1. And of course, I didn't have -9 as I'm not really using negative numbers here, but -9 can be replaced with 14. There you go. So you might figure, even if you figure out something that multiplies together to give you -1, you're almost there because you just have to insert a minus sign and it works out. So the idea is you can keep doing this. We've already got a partner for 6. The next one would be 7. I'll let you check that 7 would be partnered with 10. I don't have nearly enough room here. But that's okay. I'm just going to go ... and then I'll go down here and I'll do the rest of it. Is that okay? So I have 8. I've already done 8. I haven't put 9 into this yet. But let's see, if 5 times -9 was a partnership, then -9 should be a partner. Sorry, +9 should be a partner with -5. -5 is 18. So 9 goes with 18, right? We've already got 10. The next one that's not appearing so far is 11. Ooh, 11 times 2 would have been -1. So that tells me that 11 times -2 would be +1. -2 in mod 23 is the same as 21. I'm doing this all in my head. And I'm not really trying to go extra fast or extra slow. I'm kind of going at what my normal speed would be. If you play around with modular arithmetic enough, you can kind of make some tracks with this. Okay, the next one, let's see, 12. Now see, oh, I have 12? Yeah. Oh, I have 12. I have 12. You're right. 13. So the way I think about this, guys, 13 is the same as -10. So if 10 and 7 are partners, then -10 and -7 are going to be partners. So you just have to think, well, what's -7 in mod 23? It would be 16. So I'm not actually even calculating 13 times 16. I'm just taking 7 times 10, and I'm saying, well, if you take the negative of 10, it has to be multiplied with the negative of 7. You just write down what that was. You just kind of keep going this way. What else is missing? I guess 17 is still missing, right? 17, okay, that's like -6. -6 would have to partner with -4. And in the world of mod 23, -4 is the same as 19, right? Yeah? And I forgot 15. Okay, let's do 15. 15, in the world of mod 23, that's the same as -8. -8 has to partner with -3. Guys, using negatives can be really helpful. So -8 partners with -3. -3 would have been 20. And I hope I have them all now. 5, 6, 7, 8, 9, 10. Yeah, I've got 10 pairs plus the 2 individual ones. So that's kind of just illustrating what this claim is showing, right? Every number has a partner that's different from themselves. And so you can kind of believe it a little bit better once you see it in that form. Yes, Bobby.
So earlier in the week, we used just like that P equals 2, P equals 3. What would happen if we didn't assume necessarily P is greater than 3, but like P is greater than 2, I guess? And why didn't we start with those two implications?
So if P was equal to 3, then, well, it would be okay. It would just be that this whole part of the proof would not even apply. If P was equal to 3, then you're saying that A is greater than or equal to 2, but less than or equal to 1. Oh, well, that's not possible. So there'd be nothing here. The only part of your proof that you would have would just be this part of it, and that would be the proof. So it's mostly just so that the full generality of what's needed for the general case is on display. And if I don't assume P greater than 3, I kind of get caught up in, again, oh, there's a special case that we have to do separately. So it's just to make it flow a little more smoothly. Yeah. Okay. So that's Wilson's theorem. Yes, Omar.
Would that have to be 22 factorial by applying Wilson's theorem?
Oh, I have definitely made this mistake. Yes, because this is supposed to be P minus 1 factorial. I just realized I didn't really finish what I was saying. And obviously we don't have a 23 over here on this side. So this was supposed to say 22 factorial. The point being, let me come back and make this very clear. All of these are canceling. All of these pairs are canceling. The only one that is surviving is 22. And 22 is the same as -1 in mod 23. That's what I should have said. Good enough? Yeah, thanks for catching that. Okay, it's supposed to say 22 factorial. All right. Let's talk about quadratic congruences. This was one of the things that anybody taking a number theory class is going to have some exposure to. So we will start by just writing out sort of the general nature of it, but we're pretty quickly going to end up specializing this a little bit. So quadratic congruences, these would be congruences of the form ax squared plus bx plus c congruent to 0. And I'm going to write in mod n. I'm not going to assume anything about the modulus quite yet, but I'll say where a is not congruent to 0 in mod n. So this is what I would like to spend just a couple minutes studying. Obviously, if a was congruent to 0, we wouldn't have the first term. And at that point, you're just looking at a linear congruence again. So we've already talked about linear congruences. So this is kind of the next step up. Suppose that you have a quadratic expression and you're trying to solve that. The goal, of course, is to solve that for x. So the goal is solve for x. And as usual, I'll say if possible. In this kind of context, we should never assume that it's always going to be the case that you can find a solution. Okie doke. Well, it turns out that at least for the time being, that's a little too much too general of a quadratic expression for us to handle. So we're going to go down to something extremely specific for right now. But I promise you, one of the things we're coming back to a little bit later, a few chapters later, is the full generality of this problem right here. Okay, but for the time being, I'm going to make this a much simpler result, and it is a theorem in the book, so it's theorem 5.5. And it says let P be an odd prime I haven't made a big deal about the prime P equals 2. That's the only even prime that there is. It turns out that P equals 2 is kind of pretty badly behaved relative to all the other primes. For example, your quadratic form, so before I finish the theorem, you don't need to write this down, but you guys all know the good old, when you're trying to solve a quadratic equation, well, here's your roots. Well, right away, if you're in mod 2, if p is 2, you're going to have problems with dividing by 0, essentially. Okay, so there's some weird special cases that you would have to deal with in the case when the modulus was 2. Keep in mind, if the modulus is 2, everything in that universe is either 0 or 1. Something tells me it's not going to be too hard to plug in the possible choices for x in mod 2 and see what you can get for solution. I don't think I need a big theorem to handle mod 2, but it's just good to know that you get this kind of strange behaviors of things oftentimes when you work in mod 2. So there are a lot of results in number theory that start off this way. Just use an odd prime in the result that you're going to state. So that's what we're going to do here. And then the congruence. Okay, so I hope you guys won't be too disappointed. I'm going to reduce to this congruence specifically. We just went from ax squared plus bx plus c all the way down to like the most simple congruence of all. This is a congruence in mod p. X squared plus 1 congruent to 0 in mod p. Keep in mind, if you're trying to solve this equation in the real numbers, you would already be out of luck because there is no square root of -1 in the real numbers. Okay, but in the complex numbers, then you could use I as a solution. But we're not even in that realm, right? We're working in this weird mod p world now. And this has a solution for x if and only if, all righty, you ready for this? This is quite interesting. It depends on what the prime is, and it is the following statement. Your prime is already assumed to be odd, but specifically and more precisely, it needs to be congruent to 1 in mod 4. So if I'm trying to solve this congruence in mod 5, no problem. In fact, you could probably just plug in x equals 2 and you see that it works. But if you try to solve the exact same equation in mod 7, it won't work. And you can try every number that you want and you won't be able to get anything to work here. So it's sort of almost like approximately half of the primes will be such that you can solve this equation and half of them will be such that you can't. Later in the semester, I'll explain how you can take a generic quadratic equation and do a change of variables to it to basically convert it into more or less this one, maybe with a different. So the x will have to turn into a y or something to do some change of variables, but you'll basically be able to solve the general case by a change of variables that replaces it with this case. And so that's why this is such an important congruence. It gets its own theorem, and we're going to prove it in just a second. Is that a hand, Brian?
Yeah.
Please.
I don't know if it's intentional, but is x unique in this case, or should we say?
No, the x does not have to be unique here, and I specifically didn't mention that. And actually, you look. So I just mentioned that p was equal to 5. X equals 2 would be a solution. You could just as well have put in x equals -2, and you would also have a solution, which is a different solution in mod 5. Yeah, so that's a good note here. It's not part of my notes, but I think it's worth writing down. X need not be unique. I mean, it's not even unique in the real number case. A real number case, your congruence may or may not have a solution, but if it does, it may or may not be unique, right? So lots of different things can happen. Okay, so I would like to try and do the proof of this, which is absolutely the last thing I have in my notes for chapter 5, and then we'll do the group work, and it's going to be a nice. We're going to finish chapter 5 right at the end of week 5. I'm feeling really organized right now. That won't last long. Anyway, but yeah, let's see if we can get this done. This is not a terribly difficult proof either. So these results are relatively elementary, I think. overall. So we do have to go forwards and backwards with this proof. So I'm going to assume, for the forwards direction, I'm going to assume that A is a solution. So this would just mean that A squared plus 1 is congruent to 0 in mod P. And it is my job to prove that P is congruent to 1 in mod 4. Far so good? Okay, so that's the setup. Would you guys agree that A is not a multiple of P? If A was a multiple of P, it would essentially be 0. And 0 squared plus 1 is not 0, right? So there you go. It's definitely the case that A is not a multiple of P. So guys, we are in mod P, and we have P not dividing A. I'm going back to this Fermat's little theorem again, and we can just write it down by Fermat's little theorem. A to the P minus 1 is congruent to 1 in mod P. Okay, so we've got that. But we were supposed to come up with the fact that P is congruent to 1 mod 4. So I don't quite see that yet, but I'm going to just tweak this just a little bit. I'm going to take this P minus 1 exponent, and I'm just going to play a little game with it here. I'm going to break it up as a squared power and a P minus 1 over 2 power. And that's, of course, just exactly the same as what we had before. Obviously, this won't work now, and this will not work for P equals 2, because then P minus 1 over 2 would be a fraction, and we haven't talked about taking fractional powers of anything in mod P. So, but because P is odd, then P minus 1 is even, and so dividing it by 2 leaves me with an integer. So that is a really legitimate factorization right there. And so we'll take that, and let's see. We already assumed something about A squared, namely that it is equivalent to -1 in mod P. It is congruent to -1 in mod P. Can I just put that in there instead? So -1 is what A squared is the same as in mod P. And we get something that looks like this. Well, if you're taking powers of, so this left side is either -1 or +1. But it can't be -1 because -1 and +1 are not congruent if my P is anything bigger than 2. Let me say that again. So if P is bigger than 2, -1 and +1 are not the same. And so it wouldn't be possible for this to be an odd power of -1. Okay, just think about taking -1 times itself a bunch of times. It alternates, +1, -1, +1, -1. It needs to end up being +1. So I'm just going to say that -1 to the P minus 1 over 2 must actually equal +1. It cannot be equal to -1. Right? It has to equal +1 in order for this congruence to be true. It's very rare, isn't it, that we take a congruence and turn it into an equality. We are almost always doing the opposite. We're taking some equal sign and then changing it into, we're passing to some congruence class mod n, right? So that's normally the way this works. This is kind of reversing that trend, bucking that trend, say, oh, we know that this congruence is true. We can actually turn that into a legitimate equal sign. This is not mod P anymore. This is just, a literal equal sign. So that just means, guys, that P minus 1 over 2 is even. It is even. P minus 1 over 2. It's 2 times some integer. I'll say 2k for some k in the integers. And you guys can do the math on that. I'll just wrap it up here. P will now be, if I move things around, equal to 4k plus 1. And so, therefore, P is congruent to 1 in mod 4, as we were hoping to prove. Did you have a hand up, Kim?
Because I was like, since P is greater than 2.
Yes.
can P be written in the form 2A plus 1 or 2N plus 1?
It can be, right? It's an odd number, so you can certainly do that, which is kind of how you derive that form. Yeah, exactly. But anyway, the point is this exponent is even. So it's 2 times something. Rearrange the equation a little bit, you get what you want. Anybody got any problem with any of that? Okay, hopefully not. I don't sound like I'm very receptive to any complaints right now. If anybody doesn't like my proof, let me know. I'm more than happy to go back and try and do better. But that should be the whole thing. Okay, we have to prove the backwards direction though too. So we're only halfway done with this machine. Let's see if we can get it working the other way. So for the backwards direction, right, I'm going to assume here that P is congruent to 1 modulo 4 already. And to just kind of retrace where the proof came from, I'm going to go ahead and write it in the form of P equals 4K plus 1 for some integer K. So we'll go ahead and start off this part of the proof the same way that we were doing on the last part of the proof. And my job on this part of the proof is to prove to you that there is a solution to the congruence x squared plus 1 congruent to 0 and mod p. And what better way to prove that there is a solution than simply producing it for you? I can do that. I can do that thanks to Wilson's theorem. There's a method to my madness. We do everything in a certain order for a certain reason. And we're going to use Wilson's theorem to construct this solution. So here's my claim. Here is my claim. My claim is that if we take p minus 1 over 2 factorial. So let's just stop and make sure. Because p is an odd prime, this will be an integer, so I can make sense of that. That is a solution. The claim is that is a solution to x squared plus 1 congruent to 0 in mod. That's my claim. Okay. Well, let's actually just try to square that p minus 1 over 2 factorial, because that's obviously part of what we're going to have to do. So for the proof of this, I'm going to take p minus 1 over 2 factorial, and I'm actually going to square it. Because ultimately, I want to plug it in for x. And when I do that, I'll be required to square it right away. Okay. Well, so if I square this thing, guys, and I guess the first step at least is an equal sign. That's just going to be 1 times 1 times 2 times 2 times 3 times 3. There's 2 copies of each of these factors. The last one being p minus 1 over 2 times p minus 1 over 2. Just like so. So you're literally just making a double copy of every one of those numbers. Now I'm going to do something a little tricky. I'm going to pass. Now I'm going to do what we normally do. I'm going to take an equal sign and I'm going to pass to a congruence equation. And this will, of course, be in mod p that I'm about to do. And here's what I'm going to do. I'm going to leave the first one the way it is, but I'm going to take the second one that we have there and I'm going to rewrite it as sorry, I am going to, okay, this is going to look like I'm cheating. I'm going to change the second one to a negative 1. And then I'm going to take the second 2 and I'm going to change it to a negative 2. I'm going to take the third, second 3, change it to a negative 3. I'm going to keep going like that. I'm going to take the p minus 1 over 2, and then the second of the p minus 1 over 2's, I'm going to take it as a negative. So I left half of the factors the same, and I put minus signs on the other factors. Is that legit?
Is that because you have 2 copies of everything? So if you get one set of the copies and you reverse it, that's the same thing as putting a minus sign in front of them?
I don't know. Some of you guys are teachers already. Do you let your students just put minus signs wherever they want? I don't think so. No, probably not. I just changed the 1 to a -1 and changed this 2 to a -2. So maybe what I better do is count how many minus signs did I just put in there, because technically that would be cheating. I can't just decide I'm going to put a bunch of minus signs into this expression. How many -1s have I inserted into this product? How many specifically?
P minus 1 over 2.
P minus 1 over 2. So you know what I'm going to do? I'm going to fix it. I'm going to fix it by over here on the end. I'm going to take P minus 1 over 2 factors of -1, because I don't want anybody taking points off my paper. Okay. Which is what always happens. Yeah, so there you go. I'm going to go ahead and slip that in there. Okay, now, this is so clever. This is so clever. Now I'm going to take the -1, and because I'm working in mod P, I can change it to P minus 1. Right? And I'm going to take the -2, and I know I'm working in mod P, so it's the same as P minus 2. And then 3, and then P minus 3, and dot, dot, dot. We eventually come over to the end of this. We have a P minus 1 over 2. And I guess I want to add P to what I have here in the brackets. And that, I believe, would end up giving me P plus 1 over 2. And this is all in mod P. Oh, and don't forget, I almost got points taken off. I have to keep that -1 to the power of P minus 1 over 2 in there as well. You guys with me? That's such a clever calculation. What do I seem to have now here on this last line? 1 times 2 times 3 times 4 times da 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 da, all the way up to P minus 1 over 2. The very next integer would be P plus 1 over 2. And then if I go backwards through the alternating factors, the next one over to the left would be P plus 3 over 2, P plus 5 over 2, and da 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 da. P minus 3, P minus 2, P minus 1. Guys, this is just a jumbled up expression of P minus 1 factorial, which is what's in Wilson's theorem. So let's just write that down. This is just P minus 1 factorial times -1 to the P minus 1 over 2 in mod P. Oh, but by the way, what is P minus 1 over 2 going to be? Is it going to be even or odd? P minus 1 over 2 is even. So if I take -1 to an even power, do I even really need to write it down? I don't think so. So this one is just 1, right? And by the way, what is P minus 1 factorial? According to our Wilson's theorem, it's -1. So guys, this is actually just -1 times 1 in mod P, which is just -1. There you go. So this guy right here is -1. And if I then add 1 to it, I'm going to get 0, right? So I think I'm going to squeeze it right in here, guys. P minus 1 over 2 factorial squared plus 1 is congruent to 0. Yep, it is congruent to 0 in mod P. In mod P, which is the congruence that we were trying to find a solution for. And we've found one now. It's not necessarily unique. Okay, there might be some other way to express whatever this number comes out. It's going to be a big number. Factorials are always large, right? But there could be multiple ways to come up with solutions. In particular, the negative of whatever this is will also be a solution. So you have to keep that in mind. But isn't that a clever proof? I think it's pretty neat. And we used both Wilson's theorem and Fermat's little theorem to push that argument through. Yeah. Actually, we used the Fermat's little theorem to go forward, and then we used the Wilson's theorem to go backwards. Both of them are playing a big role here. I know you guys probably are wondering, like, what do we do if the modulus is not a prime? How much of this could go through? We've already seen that this isn't true. On Tuesday, we saw this isn't true for a non-prime. What about quadratic congruences in some other weird mod as well? That's another really hairy question. So these are much more problematic things to do if you're not working with a prime number. The importance and power of primes is pretty prevalent here. So we're going to come to a way to try to generalize this. Some of you, I think, may even know it already. There's a way to generalize Fermat's little theorem to a modulus that's not a prime. That's kind of in the next chapter. This is the end of what I have on chapter 5. So actually, this is a good chance to pause. Are there any questions so far? Okay, if not, instead of starting another chapter right away, I would like to let you guys practice what we've been doing. These are two problems. They're pretty short and sweet, but I would love to let you guys get into groups of 2 or 3 or 4 people and talk through these. Again, you want to be thinking about Fermat's little theorem and the Chinese remainder theorem on these problems. And again, make sure you factor 133 correctly, which I can't say that I was able to do successfully. Learning my lesson. Yeah, my number theory professor couldn't factor 133. Okay, once you've got 2 or 3 people, come on up and start reading these 2 problems, and I'll come around and give you guys a hand. Got you building moves though. I don't say you're a little bit more. That's the only thing that works.
That would have been instead. If I drink a coffee at home, it's just black. Oh, but. Clean this side.
Yeah, thank you. I appreciate your help, Omar.
Oh, I just drink it for the captain. I don't care about the taste anymore.
Get out of the way here.
So.
Are you all done?
Posing.
Thank you. I'll take it from there. Thank you so much. You're welcome. No problem. Okay. You guys just want to double check. No. Okay, good. I got the camera on you. This go on YouTube for the whole world to see. So no pressure or anything.
I know that we got
Hey, where's Matt? I'm using yours.
No, but this is
Okay.
P minus 1. We have this is P minus 1 and 19.
Hopefully, I hear there's some bugs going on. Yeah.
We know that GCD of A and 130 is 1. Then A doesn't divide 130. We know A doesn't divide 133 and B doesn't. Oh, that's 133. So then we know that A doesn't divide 7.
Rephrasing
And
into
that
that mod language.
So we're going to combine all those statements.
Okay, yeah.
Oh, yeah.
Rephrasing is kind of language is good. You have a partner, Anthony? You're with them. Okay.
From what he said. So
Oh, he did say it?
he said.
Okay. Oh.
So like, oh, I thought it was so I got it.
Yeah,
Like 13 times 11, I was like, no, it's not going to.
And it gets to start next to 3. So he's cool with it. This is a good one.
So I think that we just focused on the GC like 133. That's 1. So we know that. So we have
Yeah.
right. So then we want to split this statement into 2 statements. One mod, 7, 1 mod, 19.
I'm thinking,
I've got more markers.
Because from this thing, so it doesn't divide.
Oh, it's okay. We got plenty
A
in front.
doesn't divide 7. So and A doesn't divide 19.
Yeah.
7 is prime, 19 is prime.
Oh, yeah. That was good.
So then we know that A to the 18 is going to grow into 1. Mod 19 and 1.
Like
From the same statement.
It's like join the smallest thing.
Yeah,
ever.
well,
Guys, I wanna correct something here, so
Okay.
this should really be written down there.
Okay.
For sure. This
Oh,
is the
yeah,
thing
yeah.
dividing that, so, yeah, so, this looks fine, what you have here.
Okay.
I just wanted to get it written
Okay.
proper sequence there.
That's from us. This is from us.
Break it down at on set.
Also, the same for 7, right?
E was similar, we would get A to the 6. Is congruent to 1. Mod 7, and we're at B to the 6.
Oh, yeah, we do, actually.
We just look at this. Yeah. So we get A to the 18, it's still going to 1.
Oh, you can like, you have like,
One.
I said I can write it in one.
And then I think you would get Y to
Let's work in mod
And then you like convert that modulo.
Yeah.
Prime to.
That's what I was thinking.
Yeah.
I remember to trying to make this.
Yeah. Because if you have a solution to this, and if you have a solution to this, and they're the exact same solution, then let's just follow the A to the
Let's try to
18.
work in mod 7.
19 times 7.
Mod 19. Write down what you know. If I was in mod 7, which is a prime, what would you be able to say about anything to do with
Right.
powers of A
Yeah,
or
like
powers
here
of
we
B?
would cube it, get A to the 18.
We're trying to solve the whole problem in one breath. Write down the basic things you know from the results we've been looking at recently.
That being said, the factor in the 6 is going to have to 1 on 7 product of. Yeah. And A to the 19. I'm missing this. A to the 18.
This is just a model of the variable.
Right.
A P minus 1 is 1 less.
Same thing could be said.
That's for mods, that's for mods, that's for mods, that's for mods. Now, the problem here is that these powers are not the same as those powers.
Just cube it.
So you just cube it, exactly on both sides of this, and then this, and then I wanna see how you're gonna write up the punchline part. Cause there is, how do you get back to these, mod 133? That I would like you to actually try to write it down. Because right now you're talking in mod 19 and mod 7. Okay, it's like me trying to factor in.
Yeah, great. Unique then. I think it's a start, right?
Yeah.
Yeah.
Yeah, there's a uniqueness part of it. Yeah, so this is the unique solution, mod 7, this is the unique
Because like,
mod
kind of like
19.
you get the same thing.
We satisfy all.
So.
Oh,
Yeah,
yeah,
so
so
I tried to make it that way.
How do I say that?
Mod 7 is the same.
Being satisfied, in this case is because.
Six satisfies the powers are not the same.
Like power.
Right.
This case.
Power.
We're not solving them. These are congruent to each other. Not 19. It's congruent to the same element here. It's part of the 1 property. It's congruent to B to the 18. And then same here. So you get A to the 18 satisfies this, A to the 18 satisfies this, A to the 18 is congruent to B to the 18.
Then satisfies the 132.
Yeah.
Because you're looking at 8 to the 6 club.
Yes.
Right?
Yeah.
Yeah.
It's a little different. Right.
Two words.
It would mean that A18 works for both, so that means it works for the multiplication. Right.
So that actually means.
Can you talk about? So. A to the 18, so 1,
E to the 18,
mod
7, and A to the 18,
degrees.
E to the 18, and mod.
I was so that.
I was
Now,
yeah,
getting on you.
You leave them.
I was like six and one.
I want to say, once you,
Oh, yeah.
Oh, I guess. No, I wrote that in motion statements. It's mod 19, this is mod 7.
I can kind of see all the other processes. Uh-huh. Coming from the.
Should not address that.
You're good. No, yeah, I was like, I was like, oh, I'm gonna set up a system of Congress.
This is our new one.
I'm gonna set up a system of Congress.
I know.
That's what I'm gonna do. I'll just mix this up.
What, if this is my system, whatever the solution is.
Yeah.
133. What is the solution?
Right, I just said, kids,
Obviously, a solution.
which is what the goal is, right? If the P does not go into A, P does not divide A, then you're in this school.
Okay, yeah.
Right, yeah, that's Vermont Senate theorem, that if it doesn't actually,
Since this system of congruence.
it's not involved sometimes, yes, then you can do this.
Solution, i.e. these must be the same in the mod of.
I don't know why I decided one by.
And that's, and so then when you subtract.
That's why it made me think this, because of the 19 with the clear there too, and then the 18 there.
Yeah.
It's automatic.
You gotta set it up formally.
Oh, yeah, you're gonna get that.
That is very simple. Anybody need a hand?
Double check if this
You
is
can put a
correct.
double check.
Right.
Okay, so if you're gonna use, I'm gonna say by the uniqueness part
Oh,
of the CRT, just because when I see uniqueness of CRT, I'm like, oh, what's the Chinese or mega theorem not unique? The theorem itself,
okay.
it's just the wording of it. Anyway, if you're gonna apply the CRT, I wanna see a system. I wanna see what system are you applying it to? So I need to have X congruent to something, X congruent to something like that, right? I'm totally good with
Someone knows right,
with
please.
these mods that you kind of set up there. So the way I would argue is that I'm going to consider the following system. So. Now, if I set up that system, can you
Yes.
tell me an X that would be a solution to it?
133 is just.
A to the 18th, you just check that right here, A to the 18th is. Is there another X that's obviously also a solution?
That would in chapter 4. So we have.
By obvious, I mean really obvious. Say again?
Divides.
B to the 18th, right? Exactly. So these are both solutions to that. So by the uniqueness part.
Oh, yeah, I was
of the
gonna give you
CRT,
those things,
they have
divide
the
zero.
same in that box. So the rest of
But
it.
I mean, straight stories.
But if you just wanted to know, like, how can you actually formally set up the system for the Chinese remainder theorem? This would be it. You can display this and say, okay, we know this has one unique solution on 133. And then you realize that there's one obvious solution, and then there's another solution that you derived with your earlier work.
So I guess-
And so they must be the same. All right, good job. Yeah, and it's gonna be very similar for number 2. We're like, so on number 2, see if you can do a similar process. It's doing good?
I think we have an, you know, really missing the in between.
Okay.
Sure. 7 divided 1 and 19 divided 1, then the product should divide 1. That's what the other way around. That's what-
1 divides 7 and 1 divides 19. So 1 divides 133.
You guys,
Should be right there.
you guys good on this?
Yeah, but that's just, I mean, 1 divides everything. So I'm not sure that's really. So what I would like you to think about is. This one. This,
I don't watch them, but I watch
the
them.
mod 7 one, you've got this one,
And they wanted to say
Yeah,
they
this
did that it was actually satire.
right?
And everyone's like,
So if I asked you to solve, I want to use the CRT. Help myself to
Even
solve.
numbers.
I'm going to, anytime you're going to use the CRT, there should be a
It's like
system
about
of
an hour and a half.
operations.
Or a piece of value.
There
Well,
you
right,
go.
it's not prime.
Now, the CR, before I figure out what let's just remember what the CRT tells us. As long as these mods are relatively prime, which they are, we get one unique solution modulo. So there is a unique solution to this in mod 133. What are the two?
A minus or A to the 18.
Right, obviously B to the 18th, if you plug that in for X, it's like a no-brainer. But also, if you plug A to the 18th there, you've calculated already that that's true and that's true. So A to the 18th is equal to 1, both of those mods. I'm sorry. Is congruent to 1, which is congruent to B to the 18th.
Yes.
So, I'm sorry, so A to the 18th is congruent to 1, which is congruent to B to the 18th in mod 18. Yeah, so A to the 18th, putting A to the 18th in for X right here. And similarly for this one. I have two solutions. Uniqueness was of the CRT. It is, see how often it's actually exactly part I want here. The uniqueness part says, well, these can't be different. They have to be the same in that.
Minus one and two minus.
It's basically, I think, what the what.
Give me one of the factors, T minus one and two minus.
Exactly.
Yeah, I think that's what it is.
Okay. It's the whole story. The second problem is almost the same thing. It's general, but it'll give you guys a chance to practice it without running in and stealing your time.
But they're odd.
Okay,
But
great.
if one is
Oh,
odd,
yeah, how about
one is
here?
odd, one is even, it might not necessarily.
Let's see. I don't like using.
Well, it says distinct.
No, I would not use that.
Yeah, like if one was two, the other one was odd, it's not gonna buy it.
This is.
Like if one is odd, one is even, minus one is gonna make the other one odd. They have to be both up. In order for P minus one to divide.
But it tells us they have.
Yeah. We're just saying why it doesn't have to be odd. But we're worried about itself. As Tanner was saying to write them as two P plus one, and have plus one since they're off.
Just say it on time.
Then you get to say you get two K divided. K divided.
Yeah, that all works.
So we have two other primes, which is a K divided. No, it's full of. Oh, no. So yeah. So M times L. This is I feel like for these, like citing out what we have might help. Like you see, it says
Another one.
Surround that.
I mean, these doesn't divide. Such that P minus one divides.
What is that?
Yes.
Yeah.
Think dog primes.
Oh, I normally,
P minus one divides Q minus one.
In the bottom. Okay, well, that's each one, right?
And then we also know
know that
GCD
Q minus one,
Which is just one way of saying.
P minus one.
Okay.
is.
Yeah, we
You also
basically
know
have it, I just wanted to mount
that-
let you guys listen to it.
So by.
Oh, yeah, you.
We can say like the not
Right.
Yeah, the PQ doesn't divide, does not divide.
Really actually have to do that here, it's more about.
But you were thinking the,
You can eyeball it for.
I see what you're trying to do. It's
There's
one.
linear
combination. Right.
What
PQ does not divide.
Have to be the same.
I don't know.
Because like
You might be the other way.
By a little bit. They're, and the PQ minus one is congruent to PQ. We're gonna need that for sure, because we have Q minus one, one line. A to the PQ minus one.
Right.
Minus one is congruent to one.
Okay, well, again, I have another one. So it seems to me that
We're like.
I mean, if I could show.
Now, we need to somehow turn this guy into Q minus one has to become Q minus one,
If I could also
and then
show
we'll be done.
that. Then I'd go back and I would.
Okay, yeah.
Here's my CRT
Although, now,
got my system of congruency. What are my solutions? Well, obviously,
No.
one is a silver.
We know it's not prime, it's two prime.
Quite as obviously.
We know it.
Here,
Correct?
a.
Does that make sense?
Yes.
so then,
Well, that's gonna tell us that there's two solutions.
like, if PQ for
Say, so you just have.
I think I want to avoid fractions, yes.
This is great. This is not really what you have to do. One of which, by the way, is on that. In this step right here, this stuff, so, yeah, that's the only thing we haven't talked about. So I'll let you guys focus on that. Anybody need help?
Well, we're.
No. Let's go, let's just go in mod P and mod Q separately, and let's do another glue job with the CRT. So just like the first problem. So can we prove that congruence in mod P and also in mod Q separately? So that's gonna be.
Consider both of them.
And actually, this would have my red pen going crazy. This PQ is not even a prime anymore. So we can't use Fermat.
Oh, big. That's so true. Wow.
Careful.
Wow.
That's why we do group work. That's where.
Yeah.
Yeah. So the power behind these results we've been doing, guys, is that in the prime moduli, we can use this Fermat.
That'll be the grand mod P and mod Q though.
Do them separately.
Yeah.
Yeah, do them one at a time, and then I think you'll be much happier. Okay.
I think you still want PQ minus one though.
Guys, on number 2, try to work in mod P and mod Q separate.
No, it's mod P now instead of mod P.
Okay.
But no, actually, no, we couldn't use that.
Oh, actually, no.
No, yeah, we have to use Q.
Yeah, the top one should be P though.
Module works.
Like for three.
Yeah.
Yeah.
This is like some other. Huh? Well, it still has to be a P.
It still has to be a P.
So you know.
Yeah.
But we do know that.
So you guys.
I was thinking if we
I'm
had
not gonna
Q
say.
as both, then we could say that.
Like this, but you are not using.
By the Chinese remainder, it has to be the same product, right?
Yeah, but this.
Moduli that.
But this can't be Q because by modular term has to do the
When in
modular
fact, it
minus.
factors as.
Yeah.
No, we would have to show that, it's not given, we'd have to show it. Right, I'm saying, I don't know.
Oh,
Yeah. No, but I think this is like. Yeah, so from here by the insurance, I'll say.
Highly recommend.
That, then we have this times this. I want to try out the final statement, but just like work that. By.
7 analysis, just mod 7, and then start over with.
Oh, I need this part.
Mod 19 analysis.
I got it. Okay. But you run around this way. P minus one. It's the same answer. Oh, wait. I got it. Yeah, I think horizontally.
Yes.
Actually, I don't know if we could jump into it already. Because they have to be congruent in the same moduli, no? We would have to get a to the Q minus one, like what you were saying earlier. I think we want to get that statement also, but including both. We do. It's gonna come from here. We haven't used this on.
I like it.
This is just.
I like it. Yes.
Okay. You're not gonna have a lot
By the uniqueness part of CRT.
Yeah.
By the uniqueness part of CRT.
We show that this is, I think we want to do it the reverse because we want to show Q minus one, but it's the same thing.
We can also do this, that's just equal to a to the k times a to the k minus one, which is still compared to the same thing.
Yeah, you're gonna at some point need to use this. So there's Q minus one has to be replaced with Q minus one.
Yeah, so we wrote there.
But see, the thing is, so this is true already, right? So if you take the K power on both sides.
Oh, yeah.
Take the K power on both sides, then you'll get this still. But we also have this, so you have this one and you have this one. That's how you get your negative CRT. That's the idea behind it. Hey guys, we're having so much fun that I just realized that we've run out our clock again for this, not only this day, but this week. These are a couple of really good problems to help you appreciate how the Chinese remainder theorem and Fermat's little theorem work together, right? You guys have to do it that way. Put the CRT and the FLT together in solving these problems. If you didn't quite finish, the solutions are up in Canvas. I highly recommend that over the weekend you give them a read and make sure you understand these problems, okay? I am going to go downstairs. I'll hang out for a little while for anybody who's wanting to follow me down there. If it's pretty dull and quiet down there by 6 o'clock, I'm going to take off and start grading this massive stack of papers I have. So, but you can also email me. I do answer email round the clock.
Is that the stack
This is the 250B, which is the differential equation. The other thing you're out there together, so yeah, it's going to be like that. First, you didn't always. Well, I have 75. Yeah, 75. So nobody's dropped the class yet. Yeah, by the time I get to the final exams, I've usually lost about 20%. It's usually the 20% I don't want to grade.
Yeah.
So it'll get a little bit better later on. But
They drop a lot later on?
they will eventually.
Or they just stop coming?
Well, yeah, I've had more of that happening already than normal this semester. I'm not real happy with the 250 attendance, but I'm reserving judgment until I actually grade their exams. If they all ace my midterm, I'll be happy.
It's good enough to come to class.
Yeah, that's right. I can't really complain.
Yeah.
Getting it all down.
Yeah.
Okay.
So you guys do number two?
No, so I don't know that you could divide by A. Yeah, so it's not that simple. We'll talk about it. You have to do an actual change of variables to it. It doesn't work the same way you would do it if you were working in the real world system. So that's the only thing.
Yeah. I see a bunch of patterns.